To investigate the impacts of future climate change, we run idealized simulations with global climate models, which are, in a nutshell, integrations over time of the equations that describe the Earth system. In projections of future climate change, these integrations also have an additional term that represents the forcing from the emissions of greenhouse gas forcing. These models are not to be confused with what everyone else would think a model is, which is this. In this figure, I'm showing the AMOC anomaly in future climate change in a number of models, which are color-coded here. Each color in this figure corresponds to a different climate model. If you look closely at these projections, you see that there is a big range in the possible decline rates of the AMOC across the models. And this is due to differences in how models handle the representation of the ocean circulation. For example, the model down here in cyan predicts a reduction of about 75% of the AMOC strength, but the models here above in brown, it's only a 2% decline. So this is a big difference, but what does this mean in projections of future climate change? You would think because the AMOC has such big different decline rates, that should impact climate change, which in fact it does. But until recently, the exact impacts of the AMOC decline were not known because the models have only recently caught up on simulating and understanding these processes. In my work, I investigate whether these different decline rates affects, in fact, simulations of future climate change. Disclaimer, they do, and let's see how. In this figure, I'm showing the projected temperature change in models in which the AMOC decline is different. So for example, in the panel above, I'm showing the average of the models in which there is a large AMOC decline in projections of future climate change. And then the figure below is an average of the models that project at a very much smaller AMOC decline. And units here in these figures are degrees per degree of global warming. So it's scale, in other words, is relative to the global, is relative to a degree of global warming. It's pretty clear here that in the models with a large AMOC decline, there is a much smaller temperature increase in this region of the North Atlantic, which actually coincides with the region where the AMOC waters sink to the bottom of the ocean. And this doesn't happen in the models with a small AMOC decline. So this is actually a big deal that the models project such different patterns of temperature change, because wind anomalies are largely influenced by the heat released by the ocean. Therefore, these different patterns of temperature change, they cause different wind circulations, which affect projections of climate change impacts over Europe and North America, such as temperature extremes, heat waves, droughts, and rainfall. To go a little more into details, here in this other figure, I'm showing the projected precipitation change. Again, above are the models with a large AMOC decline in the future, and below is models, the average of models with a projected small AMOC decline. So when we examine precipitation change, we see drastically different anomalies in the models with large rather than a small AMOC decline. In the North Atlantic, almost the entire basin exhibits a decrease in precipitation, and there's actually an anomaly of opposite sign in the small AMOC decline. Another example is here, the precipitation associated with the Indian monsoon, which affects millions of people. And in the models with small AMOC decline is a lot bigger. There is a much larger precipitation increase than in the models with a large AMOC decline. So I don't want to go too much into the details, but the main reason why there are these discrepancies is because a large AMOC decline partly counteracts some of the effects of global warming. To be honest, I find this amazing that an ocean circulation can affect large-scale climatic events, even rainfall around the world. With so much at stake, it is really important that we work on narrowing down the uncertainty in the projections of future possible states of the AMOC. The good news is that this problem is solvable, just as not that easy. The models predict many future outcomes because they rely on internal parameterizations of physical processes, and all models have inherent biases. And by biases, I mean that in climate models, there are some differences from the real world, also in the simulations of the present climate, but there is no one model that simulates the entire climate correctly. So how do we go about solving this specific problem? First, we need to select the models that do a better job compared to observations of the real world at representing the physical mechanisms that are responsible for the AMOC to decline. But second, we also need to come up with a rigorous physical explanation for why we expect the AMOC to change in a certain way rather than the other. In climate science, we say that we need to come up with multiple lines of evidence to have confidence in our predictions. How can we leverage machine learning? From our analysis of climate models, we know that there are multiple variables in the current climate, which I'm going to call features from now on, that can predict the amplitude of the AMOC decline. One example is the models in which the salinity in the North Atlantic is large in the current climate, in a simulation of the current climate, then those models generally predict a larger decline in the AMOC. And like salinity, there are several other features correlated with the response of the AMOC to climate change. But we need to be able to tell which ones are the strongest predictors across all of the models and all of the variables that we consider. So if we construct a table of train and test data, each row will correspond to a different climate model. The tricky part here is figuring out what we need to put into the feature cells. Column of the labels, this is pretty simple because this is just the simulated AMOC change in each climate model. So this is difficult because we are dealing here with variables that have complex multi-dimensional patterns. For example, here I'm plotting one of the possible predictors, which is called mixed layer depth. You can think of the mixed layer depth as essentially showing the regions where the water of the AMOC current sinks in the North Atlantic to then make its return towards the equator and the southern hemisphere. Here in these figures, I bring up an example of two climate models. The model on the left projects a large AMOC decline, and it shows basically that in the mean climate, there is a large area of water mixing in these regions on the North Atlantic where you see the orange areas. On the other hand, this other model on the right is a model in which the AMOC decline is pretty small. And what it shows compared to the model on the left is that there's not much going on. That's like the strength of the AMOC and the mixing of the water associated with the AMOC formation is pretty small. So the problem with this is that there's not just one absolute value, but there is a complex spatial pattern. And so you need to be able to retain the spatial information in order to make a prediction of how the AMOC will decline. So this is clearly a difficult problem because all models, as I said, are different. However, there tend to be recurring patterns across these models. Hence, we use a method that is called the empirical orthogonal functions, or EOFs. EOFs are essentially a principal component analysis in multiple dimensions. In our case, we use it to extract the patterns that explain most of the variance across the models. And once we have 1, 2, or 3 patterns for each feature, then we can compute spatial correlations of how these variables look in each model with the leading 2 or 3 EOFs across all models. So this is the information that we are going to put here in the table of the features. For example, for a selected feature, say salinity, model A has a spatial pattern of 0.50 with EOF1, and a spatial pattern of 0, 1, 2 with a UF2. And we do this for all models and all features in order to be able to fill this table. And then we feed this information together with the labels and a training set to supervise regression algorithms. Out of the regression algorithms, we obtain weights for each feature. From these weights, we're able to determine which features are the most important in predicting the outcome of the AMOC. Once we have this information, we can select the few models that are best at simulating the most important features in the current climate and see what is their prediction of future climate change. Now, this approach works in our particular case because I had a priori knowledge that models that with a certain simulation of the mean climate tended to predict similar rates of AMOC decline in the future. For example, as I mentioned earlier, the models with higher salinity all predict a strong AMOC decline. What this additional machine learning and exercise adds is that now I know which is the strongest or which are the strongest features among all possible variables that I'm considering, and how the spatial pattern for each feature looks like. With this added information, I can make a better comparison between the observations and the model. And I can select the models that are better at simulating the mean climate, thereby reducing the possible outcomes of the AMOC decline. In addition to this exercise, to be sure about a prediction, we sure need to provide also rigorous physical explanations for why we expect a change in the AMOC to be small or large. And as here I also illustrated one method to leverage data science and machine learning algorithms to approach this problem, but I'm sure there are several others that could be used, including image recognition, for example. And well, with this, I'll conclude, and thank you very much for listening to me, and please don't hesitate to ask any questions and contact me if you're interested in learning further about climate science and possible applications of machine learning. Thank you.
Yeah, awesome. Yeah, Katinka, she does such a professional job of recording her model and recording her talk. And when I was listening, I was thinking, oh, Anna has a model predicting, the climate change in the air, and then Skylar's model is about the impact on human on the ground, and Katinka's model is about the underwater. I feel like we just covered the whole.
That was really done. That was
Yeah.
right. Yeah.
It was so amazing. Yeah. Yeah. Since she's not here, we can definitely post questions on the meetup page, and she said she's definitely going to take a look and answer it, and or if we have any thoughts, we can also chat it here as well. Yeah. Other than that, we still have 15 minutes. Originally I scheduled if we are interested, we can do a breakout room and we can do some social. This is also the first time we host online event. So before we would just, grab some food and social in the same room. So I'm not sure